Something must be stopping these dials from working. Maybe the wiring isn't attached at the back. I can't see very easily around the back. I know. Nope. Everything seems to be fine. Maybe it's the electrics at the back of the plane. Oh, I'll have to wait. What's going on out there?
Stella, we've got a problem for you. We've got 2 mirrors here, but there seem to be thousands of reflections.
Yeah, if there's only 2 mirrors, there should only be 2 reflections, right?
And look at this. If I angle the 2 mirrors together at one end, the object and its reflections begin to form like a circle.
Where are all these reflections coming from? Can you help us?
I think I'll have to reflect on this problem. Leave it with me. Thousands of reflections. All sounds a bit complicated. I think I better go back to basics for this one. Everything you see is a result of light traveling into your eyes. And light can only travel in straight lines, like this. If light was curved, then you could see round corners. And as we can see from this, that's not the case. And the only way we can see this light is when all the holes are lined up in a straight line. But what happens when the light hits a shiny object? It bounces back or reflects. And reflected light is still going in a straight line, but because the surface isn't flat, the light reflects in lots of different directions, and we say it's scattered. Now, if I look, will I see my face reflected?
The light rays from my reflection are being reflected in lots of different directions, and from where I'm looking, only some of those light rays are reflected back into my eye, so I can only see bits of my face.
You can see this happening when I use this flexible mirror.
If we look closer up, we can see the light rays shining directly onto the surface of the mirror. When I use this prong to bend the mirror's surface, the light rays bounce off the mirror's surface at different angles, giving a distorted image. But when the surface is flat, the reflected rays of light are parallel. They all reflect back in the same direction. And when those rays go into my eye, I can see an undistorted image of myself.
A mirror is a flat, shiny surface, and most of the light that hits it reflects or bounces back. And this can be a very useful thing, as Femi is about to discover.
My investigation is to see how I can brighten up this room. Now, it's a good job I'm meant to be meeting an architect called Barrow Macquarie, because it's the sort of thing that architects have to do all the time when they're thinking about how to design a building. And the only thing is, it's so dark in here, I can't see a thing. Time, I think, to shed some light on the subject.
Femi, good of you to join us.
Barrow, I have opened the curtains to this room and it still looks quite gloomy and dark, even though there's some very strong sunlight in here. I know you've got a light meter, so let's take a look. Now, in the sunlight, it's, well, around 300. But in the rest of the room, it's more like 60. Why is that?
Well, if you look around the room, we have the carpet on the floor, the green sofa, the wallpaper. None of it is actually very reflective. So if any light does come in through the room and hits the furniture, it won't reflect back into the room. So what I need is something a little bit more reflective.
So you could reflect more of the sunlight perhaps into the room instead of it just falling on to the carpet. Mm-hmm. So perhaps I could paint the walls white, get lighter furniture in, or even change the floor, but that's all a little bit expensive. It's going to take me ages.
Well, what we need is something very reflective.
Now, mirrors are quite reflective. Maybe I'll find myself a mirror. I'm on the case.
Sunlight, like all light, travels in a straight line. I can't move the sun, but I can change the direction of the light rays by using this mirror. All I need to do is to find the best position and angle for the mirror to reflect, to bounce the light rays into the room. Now, this seems promising.
Now this does work. The room is much brighter. Let's have a look, see what's happening with our light meter. And for the whole room, 120, so that's an improvement. A lot better.
So the room is now brighter because instead of the light hitting the dark, non-reflective carpet, it's now reflected by the mirror onto the white ceiling. And white is also very good at reflecting light, so the light is reflected into the whole room.
That's all very well, but we can't really leave this mirror balanced on a chair like that. It's not that practical. So what else can we do?
Well, there are other sorts of equipment that architects use. Well, this sort of thing, Femi, these are reflective blinds.
The blinds act like lots of little mirrors. The sunlight is reflected by the blind surface onto the ceiling, which then reflects the light into the room.
Well, that works really well for a small room like this, but what can you do for somewhere bigger?
Well, a little bit of know-how.
This is Manchester Airport, and thanks to mirrors on the roof, they have sun inside the terminal building.
Whoa, is this lighting the whole of this area just by using the sun?
Well, actually it's not, but it is helping an awful lot. What the architects did was that they introduced a heliostat on the roof.
The heliostat is a moving mirror that follows the sun's path through the sky, so that it always reflects the sun's rays onto other mirrors, which then bounce the light down into the chandeliers, helping to light them up.
Well, I have to say, it is an incredible piece of mirror work.
It's not bad, but it needs a clean. How about it?
No, he's kidding me.
So, reflections are light rays bouncing off the surface of an object, much in the same way as this ball bounces off the cushions of the table. Now look at this. Where do you think this ball is coming from?
Seems simple enough. The ball must be coming in a straight line from where Boffin is sitting. Well, in fact, you were watching a reflection of the ball, and the ball originally came from me, and I'm here on the other side of this two-way mirror to Boffin. The two-way mirror allows you to see through it and see a reflection at the same time. As the ball moved towards the mirror, all the light information from the reflection reaching your eyes made you think that it was coming from a position behind the mirror.
If you think of the ball's path as light rays coming from me, they reflect.
But if we draw them back to where they appear to come from,
this is why a reflection seems to be behind the mirror. The eye is seeing reflected light, and as light travels in a straight line, the light appears to come from behind the mirror. And where it appears to come from is called the image. Now, I know I'm not really back here. It's just where I appear to be. You can have even more fun with two reflecting surfaces. By having another mirror at right angles, you can see three images of the ball. Decrease the angle between the mirrors, even more images. The smaller the angle between them, the more reflections there are. And that's why there are so many images of the ball. Each time the light reflects, another image is produced. And if they face each other, there's an infinite number of reflections. So when you know what mirrors can do, if you use them properly, you can have all sorts of fun, as Femi is about to find out.
This is Wilton's Music Hall in the East End of London. It's the birthplace of one of the most famous illusions in the theatre, Pepper's Ghost. Now, I'm going to investigate it, and I should be meeting Brian Daubney, who's going to help me, but I haven't seen him yet. Brian, where are you?
Hello?
Spooky.
Actually, Femi, I'm over here.
But how come? I thought you were over there.
It's an optical illusion. It's called Pepper's Ghost, after Professor John Henry Pepper of the Regent Street Polytechnic, who 140 years ago invented it. And it was presented here in this very theatre. It depends on the fact that glass not only lets light through, but also reflects it. All glass can be a mirror if it wants to be. And that's exactly what we were seeing just then. Let me explain how it works in more detail. The principle behind Pepper's ghost is very simple. If you're walking down the street outside your house at night, then the windows of your house are usually reflecting the whole street and you back. But if somebody turns the light on inside, then suddenly you're looking through the glass and you're seeing them. And I think that's what Pepper probably realised. He could have been travelling on a train, they'd only just been invented. Goes through a tunnel and he can see the whole carriage. And they go out of the tunnel and he can see the countryside. Is the image still in the glass? Yes, it is, but you're now looking at the countryside or a station.
OK, but how does that create ghosts on stage?
Ah, come with me.
Well, obviously, there isn't a flame in this water. So, this must have something to do with the piece of glass and the candle burning over there, Brian.
Exactly. It is Pepper's ghost once again. All we have to do is to lower the light on this side and the tank disappears. All you can see now is the reflected lit candle through a sheet of plate glass at 45 degrees. Bring the light back up and you can see a single candle, wet, but with the superimposed image precisely over it, and our eye doesn't distinguish between the two.
The illusion works because of very careful lighting and positioning of the two candles. The glass has to be at 45 degrees, so that anyone looking straight at the candle in the tank will also see the reflection, the image of the other candle's flame. Both candles have to be the same distance from the glass, otherwise the reflection of the burning candle would be bigger or smaller than the one in the tank. Finally, the viewer has to be in the right position, because if they're not looking at the illusion straight on, the effect is ruined. And Pepper's ghost works exactly the same way, except on a larger scale. But if the lighting is set up correctly, and the audience are watching straight on, the effect can be really spooky.
But do you know what, Brian? In the world of TV techno know-how, it's not that difficult to make you look ghostly. In fact, I can even make you disappear. Goodbye.
Which hand have I got the racket in? Right or left? Left? No, I've got the racket in my right hand and the ball in my left hand. But looking at my reflection in the mirror, it looks like the other way round. I've got the racket in my left hand and the ball in my right hand. It's back to front. So why is that?
The light travels in a straight line towards the plane mirror and bounces straight back out again along the same path. So I'm literally looking at a mirror image of myself. In the mirror image of me, right becomes left and left right.
If I hold up this word in front of the mirror, the same thing is happening. The word is the wrong way round. So which is which? Am I the real Stella, or am I the image of Stella? When your mirror or shiny surface begins to bend, all sorts of interesting things begin to happen. Look into a large spoon, and on one side, your reflection is squashed, but the right way up. Now turn it round, and you're upside down. What's going on? I think I'll let Femi investigate that while I get back to the plane.
Many years ago, when people wanted to look at the stars, they used one of these, a telescope with lots of lenses in it. Astronomers don't just use lenses, though. They use specially curved mirrors, a bit like this one. But why? I think an investigation is in order.
So I've come to see astronomer Dr. Sue Warswick, who, with the help of 2 parallel lasers, is going to show me why mirrors are so useful.
The mirror we have here is curved inwards and it's called a concave mirror.
So what can a concave mirror do?
Well, if you look here, we have the laser light coming in. You can see it's reflected inwards and is being brought together. If I move this card along the light beam, you'll see that the light crosses over and, in fact, then is upside down.
And that's what's happening when Stella looks at the inside of her spoon. The image she was looking at was upside down, because the inside of the spoon is a concave mirror, and the light rays from her face have been turned upside down, so that the top becomes bottom and the bottom becomes top.
But the point we're really interested in is when we get to this place here, where all the light is concentrated together in one spot.
Now, how can you use a mirror that concentrates light in astronomy?
Well, if we go out into the lobby, I can show you an example.
So, Sue, why have you brought us here?
Well, Femi, can you see the map on the wall over there and all the countries in it?
Well, I can see the map, but not that much detail. It's a little bit far away for that.
OK, well, this is where our concave mirrors start to come into action. The one we have behind us here is like a bigger version of what we saw in the laboratory. And the light coming from that map is concentrated by that mirror. And if I hold this card up, what can you see?
A small image of the map over there.
And where the image of the map is sharpest is where the reflected light rays cross over, just like in the lab.
It's very bright considering the light's travelled all the way over here and it's been reflected.
Yes, and if you look with this magnifying glass, you can see that all the detail is there as well. Now, this is where our mirror is coming into its own. We have bigger mirrors than this in telescopes, and they produce images not of a map 10 metres away, but of stars and planets that are millions and millions of kilometres away.
So next time you're looking at the concave mirror in your bathroom, just think of the 8-metre wide versions that are looking into deep space.
Well, that's the dials working again. Just a fuse problem. Now, here's something for you to think about. Concave mirror with a £1 coin in it. I'm going to try and pick up the coin. Easy. I can't. Why? Well, the real £1 coin is under this card. So from this angle, what's going on? What am I seeing?
She didn't really try to grab it.
Yes, she did. That's some kind of illusion. That bowl's acting like a curved concave mirror.
So the light from the coin is being reflected. So what we're actually seeing is where the coin appears to be.
Oh, right. So she's actually trying to grab the reflection of the coin, not the real coin.